Visualize the invisible. See how atoms split energy levels with Zeeman splitting. In this problem, we're tasked with to consider the 8 n equal 2 states of the form 2LJMJ, find the energy of each state under weak field Zeeman splitting, and construct a diagram like figure 710 to show how the energies evolve as 𝐵_external increases. Label each line clearly and indicate its slope. Okay, so a couple things here. Zeeman splitting and the Zeeman effect are very important to us for several reasons. The first, and why we care, is that it provides direct evidence of the quantization of angular momentum in atoms and the existence of electron spin. You know, the thing that we've been yapping about all book. But it's also important for another reason. What other effect does this allow us to measure? That's my challenge. Now, within this, we have a lot of things to consider, so please don't forget about the PDF to follow along. There's a review of the quantum numbers there because with n equal 2, the quantum numbers definitely bounce around, and it's a helpful guide to see what we're going on. The relationships between the principal, orbital angular momentum, spin angular momentum, total angular momentum, the magnetic number, the spin number, all the totals that can come in that, this, that, and the third. So check that out if you want it. Um, I find it's really important to go back and review old definitions sometimes just to keep our heads clear, especially when we're talking about how these things are joined in linear combinations. Further, because of the Zeeman effect, we have the weak field, the intermediate field, and the strong field, which all depend on how the internal magnetic field is. And in this case, the weak field, 𝐵_external, is larger, so we have to be careful. But with that, it's very cool to see how this thing actually generates the lifting scheme that we've seen possible in previous encounters. And this time you'll see on the graph, like we did in the very opening, and we'll see at the very end, exactly what that lifting scheme looks like. So, if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. So with that, let's dive in. All right. So stop number one, it for the n equal 2 state of energy, we have a lot of quantum numbers moving around. So that's what this table is to represent. The starting point for the quantum numbers, which we will definitely need. Okay? So if our principal level is 2, right? That leads us to 8 possible levels that we could attain with our normal quantum numbers. Here, L being the orbital angular momentum, we can be the set of numbers up to n minus 1 starting at 0. So since n equals 2, we can only be up to level 1. Okay, so 0 and 1. And then for each of these, we see that we have m sub L, which needs to be careful for the magnetic number. Okay, so remember that n sub L can be plus or minus L in integer pairs. So for 0, we can be plus or minus 0, okay? For 1, we can be -1, 0, and +1. That's our set of numbers. And then for each of these, we see that the magnetic spin number, right, that can be plus or minus 1, and that's due to the fact that we're dealing with an electron, right, and that had a spin of 1/2. Okay, remember fermions and 1/2s, not bosons and integers. So with each of these, that's why we see that we have 8 here total. And then from them, we can extrapolate the orbital angular momentum with the spin momentum and see what their totals are. Okay. Now remember, this is typically the definition for J, right? But we also saw in the selection rules back in chapter 4 and then coming back to light in chapter 6, how we had the magnitude of all the possible combinations of spin, hence the L minus S column here. And then if we add the magnetic and spin numbers here, we see that we get the red combinations, and that will be used in the next part as well whenever we line up the different combinations of these states. Now, it's important to remember here that the quantum states in a system can be described as a linear combination of these 8 states. However, in the presence of spin-orbit interaction, if one wants to describe the same system by 8 states that are eigenvectors of the Hamiltonian, i.e., each represents a state that does not mix with others over time, we should consider the following 8 states, which are given here. These are the linear combinations, and we see that they don't mix over time, and it's very important that we distinct from what are the possible numbers and their combinations with what are the possible linear combination states. So here is the J value, which again we kind of saw was L plus or minus 1/2. In a lot of books, it's just L plus 1/2. But the absolute value allows you to range it over the -2, but it should still be positive. Um, and we also saw that J had another definition here, which you'll see in the PDF. But with these, this allows us to find what M sub j is, which is either the plus or minus of the j's, which we saw from just like the magnetic number ml, which was plus or minus L in a set moving by integers, or we could just add up the angular momentum number or the magnetic number and the magnetic spin number, and we see that we get the red column here. But the way we combine them, I give the reason for here. And again, you can find these 8 states online, but it's very important that we see that these are constructing the linear combinations. And if we want to construct the state, which is the ket, where we have N, L, J, and Mj, the reason why is because the formulas for the energy rely on J, M, L, and N. So it makes sense. So here are all the possible combinations, and that gives us the states that we're looking for as a linear combination with everything that we have as far as being the eigenvectors. And that becomes very tedious to find and very tedious to make. So be very careful in setting this up. Spend as much time as you need on this, because if this is wrong, then anything you calculate with the energies is going to be wrong. Now, I'd like to point out here that all of these green are the same. We see that we have 0 for L, and 1's for L here. And then we have 4 1/2s and 4 3/2s, okay, for the J. That'll be very important to us. And then, of course, we have plus or minus, plus or minus, plus minus, plus minus. With that, be aware, because those plus minuses will come in later, and we will see exactly how here shortly. All right, so now that these tables are done and we have all the states that we can actually use, let's calculate the London or Landé G factor for these states. Note that these factors depend on J, L, and S, so organizing them in terms of J and L arrangements would be beneficial for this factor. Additionally, since the total energy is the fine structure part and the Zeeman contribution, the fine structure energy depends on N and J. So organizing by set levels based on these parameters is the game plan. And that's kind of what we see going on here. And if we want to calculate the G factor, we have to use equation 7.78. Okay, and by color coding, we can see exactly what that is. We have the J state that goes here multiplying, and then we have something to do with L, and then we have something to do with S. Okay, again, for an electron, the S is 1/2. So if we go ahead and plug everything in, and then of course in the denominator we have the J's. So even if we just use a calculator real quick, or we just do some tedious simplification, we see that for these two states where L is 0, we have a G factor of 2. When L is 1 under the same J conditions, we have 2/3. Okay, and that will become important when we look at the Zeeman contribution. For the fine structure contribution, we have equation 7.69 to help us with that. And we see here that this is the N and J levels, so that's why splitting them up into sub-energy levels like this is so important and just easy to keep tagging along. Of course, you could just theoretically do charts all day, but that might get a little cumbersome. That being said, with this, we see that the fine structure term has the -13/6, so the Bohr energy, so E1, over N squared. Okay, and so we see N here, Then we have the bracket term for the expansion with the fine structure constant over n squared. Then we have n over j plus 1/2 minus 3/4. So clearly, 1/2 and 1/2 make 1, so we have 2 over 1. Finding a common denominator to minus a 3/4 gives us 8 over 4, and that's where we get the 8 minus 3, which gives us 5 over 4. Everything else simplifies. 2 squared goes to 4. 4, we see that, no big deal. 13.6 divided by 4 leaves us with 3.4. Easy enough. And then we see that we get 5 over 4 times 1/4 gives us a 5/16 or alpha squared. So that's our fine structure for these 4 states, and that we will definitely see come the graph. And we see that this is what's going to shift the 2 initial state separations of n and j, and then we'll see another state shift when we get to the j equal 3/2, which we'll do now. Oops, so the checkpoint here for stop 2 is that we have the nj sublevel 1, which is just n equal 2 and j equal 1/2. Naturally, now we have to progress this to n equal 2 and j equals 3/2. Let's see how that is. Running straight into stop number 3 then, we can clearly calculate the g factor for all of these states because everything is j equal 3/2, everything is L equal 1, and we're good to go. So if we plug this in and run it through the calculation, 3/2 for j, 1 for L, s equals 1/2, we simplify down, no big deal, we get a g factor of 4/3. Again, this is done by using equation 7.78. No big deal. Now, the fine structure part for this is slightly different, as you would imagine, because our j value is now shifted to 3/2. So if we repeat the last calculation of 7.69 and plug in 3/2, we see here that we get a 4 over 2, so we get a 2 in the denominator. And that's what we see replicated here. Make this a common denominator, you get 4 over 4, so then 4 minus 3 gives us 1. 1/4 times 4 gives us the 16 that we see here. And then, of course, 13.6 divided by 4 simplifies to 3.4. No big deal. So that gives us the fine structure contribution for the NJ set level for the second set level we see. Now, with all of this, get ready because now we have 8 energy corrections to look at. Let's see what those are. Brings us straight to stop number 4. And so we have the, now that we have the fine structure contributions, we also need to find the Zeeman corrections. Okay? And recall here that the Zeeman correction came from equation, let me go find my notes. Yeah, equation 7.79, okay? And that was a very, not that surprising of an equation because it was just, mu b, the magnetic moment, and then we have the g factor, the external field, and the mj numbers. But with that, we see we get something pretty unique going on, and we'll see that again, that red column that we saw earlier comes to play a very specific role. Here we have the fine structure contribution. Let me change colors real quick. This is the fine structure, and this is the Zeeman. Okay, and so we calculate the fine structure for set level 1, and we see that we got 5/16, so the first 4 should have 5/16 on the alpha. The second 4 should have 1/16. We have that pretty well simplified. The Zeeman correction, though, if we have the g factor of 2, we need the first 2 states, so 2 and 2. And then we saw that the mj's were +1 minus 1/2, so we get the plus or minus there, cancel the 2's, easy enough. And then we see that the mj actually gives us the sign on the correction. So we have a plus minus. That looks like it's going to lift us and sink us. So the lifting scheme is coming to fruition just in the simplifications. Similarly, the g factor for the next 2 states was 2/3. And then again, for m sub j, we had plus or minus 1/2. Cancel the 2's, we see that we get a plus 1/3 minus 1/3. Now these coefficients on the mu b term will become the slopes that we see in the graphs. So if we look at the g factor for 5 through 8, we see that we get a 4/3 in all of them, and the 3/2, the 1/2, and -3/2, they all cancel parts of the G factor term. So lastly, we get +1/2, -1/2, +2/3, -2/3. So this is the lifting scheme that was talked about in the book. And now we see that if we simplify this, we get a wonderful table of all the energy corrections and values for the Zeeman effect with the fine structure correction term included. And we see that for each state that we have, we see what their correction is. So this is more of a summary than anything else. But now that we have these energies 1 through 8, we need to go ahead and graph them. So summarizing it like this keeps it nice, tidy, and guess what? Python, Mathematica, C, they love it when you can organize it like this. So let's go ahead and check out what the graph looks like. That brings us straight to stop number 5, our last stop here. And we see that in this colorful graph from Python that we have the Zeeman effect for the energy shifts for the n=2 state. Now this is strictly Zeeman, right? And we see that we have 8 states here as we initially defined back in stop number 1. Okay, we did not break it down into the NJ or NLJ, MJ notation quite yet. But what we see here is that each of them lifts by a certain amount, right? So this one lifts a certain amount, has a slope that's paired with this slope, this line with this line, this line, this line, this line, and this line. And this is the lifting scheme that we see. But since this is just the Zeeman effect, we need to also include the fine structure. Let's see how that looks. And so here with the fine structure, we see that we get the energy set for what was that? NJ for the first set, right? Where we had 2 and 1/2. Here we have 2 and 3/2. And you see how they separate the energies by that amount due to the fine structure. So we have a vertical shift in them thanks to the fine structure. Now, if we paid attention and we saw how the red simplified in the Zeeman correction, we see that the lifting scheme comes from the fact that the G factor with the M sub J factor equated to the slopes that we see here. And that's pretty darn cool. We got some great pairings going on. 2, -2, 2/3 of -2, 1, -1, 1/3, -1/3. And of course, this is the fascinating part of the Zeeman effect itself. No one would have thought initially when they were diving into this that we would see these. But with that, we actually graphed everything pretty quick and easy. It just took a lot of setup work. And I'm promising you it's going to look a little more crazy here soon when we have to deal with the other effects altogether. So please be aware that this is only going to get more messy. Use tricks like tables to help you get organized, because otherwise, when we have to deal with these weird parameters where we don't have values for mu and b yet, or we're tasked with graphing them with respect to mu and b, or alpha for that matter, it's going to look very crazy here soon. So just be aware, it will be sloppy, but tables will help you. And then the graphs look very fascinating. All right. So, in summary, you know how fun the Zeeman effect, at least in the weak field, looks and how messy it can be on the cleanup side. So, please be very careful with that. That being said, I'd like to welcome the new patron, Richard. Appreciate you and all that the rest of the patrons have done and supported and the kind messages. I need to give a massive thank you to all my supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for access to supplemental material, current and future projects, and one-on-one help. New content is posted weekly to fuel your curiosity. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.